All right, so this is our next oral talk, keynote talk. It's my great pleasure to introduce Xiaolong. He's an associate professor at UC San Diego, where he leads a research group that studies computer vision and robotics. He's worked on a broad set of topics ranging from SSL, video understanding, dexterous manipulation, teleop, and many, many more. But in particular, Xiaolong has taken a leap of faith into the world of humanoid robotics. And what better way to train policies for humanoids than by learning from what humans do in egocentric video? So yeah, thanks for being here and take it away.
All right. Thank you for the introduction. So I'm going to talk about one of our recent work. So this is actually a title of the paper as well. So the dash in here can actually be like referenced by Google Scholar. So it's more about how to leverage human data to train humanoid policy. But before talking about that project, I would like to start from actually teleoperation, since this is what a lot of people are doing nowadays. So you can sort of see, actually when you're doing teleoperation, the human motion and the robot motion, they are sort of the same. It's really just a 3D transformation away. So the work we did for this open television project is actually, I think, a very nice feature is that it streams the robot view in real time into the Vision Pro, and then the camera can actually move as long as the Vision Pro moving. So the robot actually see the back of the head of student, and then the student can actually see this same view from the VR glass. So this enables us to do some cool applications, such as you can teleop the robot at UCSD from MIT. So this is one of our collaborators, currently a postdoc at MIT, that is actually using our robot at UCSD. So basically the video is streamed from the robot's view in real time into the Vision Pro far away, and then Vision Pro is capturing the hand poses and then do retargeting to control the robots at UCSD. So this basically is like, he will stop by this because this is essentially the pose we use to stop the process of the teleoperation. So here are some imitation learning results that you can collect data inside these scans. We didn't collect a lot of data, so this is pretty much a very narrow, no generalization case of teleoperation. The video I really like in here is actually, because we are in the egocentric video workshop, so I particularly like to emphasize the observations space in here, right? So we are completely taking only egocentric view as input, and then it's not the actions of the policy is not just hands, it's heads as well, right? So you're outputting how the head is moving as well as you are doing the manipulation. I like this video a lot because this is essentially almost the same as all the egocentric video, like Epic Kitchens, Ego 4D. It's just the difference is just the hands are robot hands now, not human hands. And a little bit of detail, actually, I want to emphasize. This is also a teleoperation results. Is that this particular task, like putting this small ear plug into your small boxes, we in parallel have 3 different teleoperation systems developed in the lab because we have a lot of people. So essentially, this is the only one that can do this task. So actually having this egocentric view from robot and stream to person is quite important for the teleoperator to conduct this task. So this cannot actually be done by just teleoperating one person standing here, a robot standing here. If you do like third person teleoperation, you cannot actually solve this task. So here is just showing some power grasp, more like a lot of people in vision have done 60 pose estimation of this driller, but no one has actually used it. So that's why we also show that you can actually use the driller. And a lot of examples of more precise control. So essentially, with egocentric view, you can actually do this kind of very precise insertion in here. As we are developing this system and experimenting with it, we do find it's incredibly tedious and also a little bit painful to wear a glass for hours, and then no one actually can wear it for hours. Usually 20 minutes, so then to collect data, it just takes a lot of time. And then we basically, as I show in the very first video, if you see how people doing teleoperation, right? So it's human controlling the robot doing things when they are doing the same motion, essentially. So that's really, from the observation space, it's all egocentric view. From the action space, they are almost doing the same motion. So there's no reason why not we can combine this data and co-training human data and robot data together. So that's essentially what we try to do. So essentially, we can actually record videos. We didn't use general egocentric video yet because that's still a little bit challenging for us to learn from. And we basically collect data that human and robot doing the same task. And at the same time, the device we use to collect the data, so before is actually, so here are some more illustrations on what kind of data we use. So essentially, the dream always is learning from large-scale intellect human videos. But at the same time, a lot of intellect videos are not really that useful. That's why we create all these, the community creates all these egocentric view videos and more task-oriented, essentially. In this particular case, we are, in some sense, we are simplifying these videos as well. So we try to collect the data set that is aligned with what the robot is doing, right? So this is actually all, like, all the data is aligned with exactly what the robot is going to do, and is collected by wearing a vision probe in here. Of course, right now we can also have a Meta Aria glass wearing the glass to collect similar kinds of videos. But at that time, so we basically find if you collect humanoid robot data, it takes maybe a month to get 1,000 trajectories with a few people. And then with human data, you can actually easily get 30,000 trajectories almost like in 2 weeks. So the efficiency of collecting data is much, much faster, and you can go to many diverse environments to do it. So we show some examples that you can actually go to many different places where the glass or VR glass to collect the data. So essentially, if you have Vision Pro, you have enterprise license, then you can use the main camera assets, which is can record video from the main camera. If you don't have the enterprise license, then you can actually do a sticking Z camera on the Vision Pro to record the video. It's a little bit strange, I know, but that's actually a lot of people do. So essentially, you can collect data like this, and I just want to show, in some sense, it's quite aligned. So the transition is from human to robot videos are actually quite aligned. And the good things about the device that we have at the time is basically you can do very accurate hand pose estimation. So the embedded hand pose algorithms from these classes are now actually pretty good. So you can get very smooth and very accurate hand poses. So that's quite important for us. So once you have this data, so we basically try to train a policy on top with human data and robot data. One thing I want to emphasize, this is not a robot policy. I actually call this is more like a human policy. So in the input and output action space, it's actually all predicting what human will do, okay? So we are trying to convert every robot's like parameters and action space into the human space. So essentially, we have these like robot observations that is like collected by teleoperation, but then we actually convert it back into the human hand pose and the wrist pose of 6 stuff is wrist pose, like completely like human representation, right? So, and this is the input, and the output is also going to be future what the human hand will do. So we are trying to convert everything, no matter what robot it is, we aligned it back into the human space. And you might think that actually this is a little bit strange in the way that you have human teleoperator, you do teleoperations and you use inverse kinematics retargeting to get the robot actions. And then now you have the robot actions, you do forward kinematics back to the human actions. So why not just directly copying the human teleoperator actions, right? So it turns out there is some errors when we are doing the IK, so it's not completely accurate. So if you directly copy the human actions from the teleoperations, so the error have been accumulated. So we find it doing better to directly go from the robot data back to the human data using forward kinematics. For the human side, we do observe basically when we are teleoperating the robot doing things, we have been extremely careful, especially for the hands we are using. It breaks every 2 weeks almost. So we have been very careful when we are doing things. So it's very slow. But then when we are having human collecting things, we are being incredibly fast. So we kind of just, because we need to align this data together, so we are basically just slowing down the human videos by doing some just temporal interpolations. It's more like 4 times slower we are making it to align these two, the speed of these two kind of videos. To just give you more sense on what we are doing, recording as the input, right? So as human videos, you can have these 3D hand poses on the right together as the input. So that's human hand pose. And then for robots, essentially we can do the same thing. With these robot hand joints, we can do forward kinematics to project it back into the human hand pose and wrist pose. So that's actually in the human hand pose space. So essentially you can see it's almost identical. It's just the pixels are different, but the action space we align back into all humans hand space. And then once you have these inputs, so essentially when you have a robot input, you have robot frame and human hand pose as input together. When you have human data input, you basically have human frame and the human hand pose as input. So every pose, every state are in human space. And then your predictions of this transformer output is predicting what are you going to do next as a human. So what is the human hand pose is going to be in the next time frame. So this is predicting what the human is going to do. So that's why we call it a human policy. It's not really a robot policy. It's a completely human policy. That's what the human hand is going to do in the next time frame. Once you have what the human hand pose is going to do in the next time frame, you can essentially going to do a lot of inverse kinematics and retargeting and control the robot to do the things. So you can sort of imagine this legwork itself. You can imagine as the legwork itself is a teleoperator. Okay, so the legwork itself is a human teleoperator that is going to, you can do retargeting inverse kinematics to control what the robot is going to do. But it is just an automatic, like autonomous teleoperator instead of a human teleoperator. So in some sense, we are training a teleoperator instead of training a humanoid policy. So the supervision can come from the robot data and also come from the human data as well. But essentially, I think the core idea in here is to forget about what robots are using, forget about all robots, just care about align everything into human representation space, okay? So if I want to use this legwork for different robots, essentially, then I can just do different inverse kinematics. We have H1, we do inverse kinematics for H1 robots, and then we have G1, can do inverse kinematics for another robot differently. So this is actually allows cross-embodiment experiments. I will show one result later. In this work, we are collaborating with CMU people. So essentially, we have the H1 earlier, and CMU has the H1 later. Between different versions of the humanoid robots, they're slightly different. The structure of the arms are different. So the same policy basically can work on both robots by doing different inverse kinematics. So we call this sort of cross-embodiment. Right, so the idea is really try to align everything into the human representation space. Right, so there are some numbers in here, but essentially you can only look at the final column, basically showing that for out of distribution data, right? So you can have different objects and different locations and different backgrounds mixing the human data training allows it generalize better. So we can really only have very limited data and interactions with real robot data. But then adding the human data in here increase the distributions of how the object can be, the types of objects and different backgrounds. So that has been very helpful for generalization. So here are some examples on, so I would say we are on purposely structure the experiment this way to show generalization, right? So you have basically 3x3 paths, and then each location represents where you can put your objects. So this is for convenience for evaluation. And then you can see on each grid, 3x3 grid, there's like 2 small boxes on the side. It basically means that the objects will be placed a lot on the right side of the box where 779 is, and then it has been rarely placed in the left side of the dotted boxes where the 065 is. So this is basically showing that if we collect robot data in just these 2 small boxes, a lot of times on the right side, and then we train a policy on top, and then mixing with the human data as well in training. So the first result is basically showing that if you train with only data in this way, with only robot data, it doesn't really generalize to other locations. It has 70% success rate in the right dotted boxes, but then very bad on the other box. And on the right, it basically shows that mixing up with human data allows you to generalize to different locations better. So here is one example on how it works when you success, when you fail. It's still very like simple like task we are doing, just some pick and place. But actually, when you are training on very small number of data, it is incredibly easy to overfit. Like on the left example is just grasping in the air, because a lot of examples are collecting to grasp things in these locations. So you kind of just get used to do this grasping. And then if you are able to, so this experiment is actually doing manipulations like swapping cup from left to right, right to left, left to right, doing this. And then when you are training when you're collecting the robot data, is all on clean backgrounds. And then when you're collecting the human data, you actually have very diverse backgrounds and different scenarios. So we are testing that actually without collecting robot data with diverse backgrounds, if you can do co-training with human data, you can generalize to all these manipulation in diverse backgrounds. And here are some results on just like grasping with diverse objects. Again, some of the objects are not actually collected from the robot demonstrations. Right, so pouring is another example that we show. We can grasp the bottle in different locations and do this pouring thing. So this is just wait for it. So the task, again, I made this very simple. It's a little bit silly, but essentially it shows we want to have a proof concept on merging the human data together can help generalization. And then the final example is basically actually we have like H1 from CMU Guanya's lab as well. So the two H1 actually look slightly different. They have different structures for the arms because we ordered them in different times. And then the single policy can actually work for both cases because we essentially align everything into human action space, and then we just do retargeting and inverse kinematics to generate actions for different robots. Right, so the words, so the text I put on top is saying it's new, but not really that new. So we have been actually exploring this space for quite a while. So this is actually the first robotics paper I published as a faculty. So the paper got accepted at ECCV 2022, but it's actually done in 2020. So that's almost 5 years ago. At the time, this is basically the scene is too easy for computer vision people, right? So we are actually collecting data in these like green backgrounds, and then do hand pose and then retargeting and get robot data. And I think from the vision community perspective, it's like, what are you doing? You are still doing a green background thing. But it's actually quite challenging at the time that even these very clean backgrounds, the hand pose is not really working perfectly because there's also occlusions from the objects, and objects are actually even harder. Object pose are still very challenging. So what happens now and then, right? So we do find that hand pose estimation is much better now. So the videos I showed before as well, like over the years, this is keep improving. And then at the same time, actually, I still find object pose estimation is not very good. Like the 60 object pose, when you have occlusion, is still a very challenging task. But then we kind of get around this. We don't use object pose anymore in these works. We just take the RGB inputs or the point cloud inputs for other projects, and then use chain topology on top. We don't have to first estimate object pose and then use it as an input. So we kind of get around that. And then now we have, of course, a better legwork, right? So a better system now, to the infrastructure to collect data, and then also a better legwork, like we all use transformer for different things. So the challenging things that is challenging before, but not now, is basically we have both two modality of data, like two domains of data, right? So one is robot data, the other is human, like RGBs. So the RGB are actually quite different. So how do you have a large capacity legwork to consume both sides of data? So that's like is much better handled right now. So in some sense, what I try to say is that I want to claim that what we are doing is new, but it's really not really, right? So it's a lot of things is more about because the community is progressing, all the tools are getting better. So essentially then we are trying out the old idea we do, and then we can, it's not working before and now it's working now. So a lot of these contributions are more coming from the development of the whole community. And then I got to talk to, I think I was in ICRA, and then I talked to Kazu, some guy now is in MSR, and then before he was in CMU. And then he showed me this video, so I was very impressed. And then I want to show it as well. So this is from 1994. It's to learning from observation. So you have humans putting a blocks on top. And like basically this is actually trying to do segmentation. And then after doing very long process of segmentation, it localizes object, and then the robot can follow what the human demonstration do and do the block poking. So again, I'm just saying that, of course, this is a system that does not generalize well, but I think the same idea has been circling around even very long before. And a lot of this progress right now, right, we see actually is in the vision side. Looking forward to what should we do? So I do think that, like on one hand, collecting egocentric video data allows very rich data, realistic data, and rich scenes. But at the same time, there is a limitation of the work that we do. Basically, it still stays in a lot of grasping, pick-and-place tasks, right? So where the contexts are not so necessarily needs to be very accurate. And I think like increasing more simulation data will be important. So this is examples actually the whole body control models that we did recently that basically is doing teleoperations, but not just like the tabletop, but also using the full body of every joint of the robot, so you can actually bend down and then reach to different locations when you're doing teleoperation. So I'm probably going to skip the detail of this technology we are doing because it's not really relevant to egocentric. But this part is relevant because essentially we are still doing streaming what the robot camera can see to the Vision Pro, right? So the teleoperator actually is remotely controlling the robot from another side to basically, so you can observe these things and then do very precise insertions to the dishwasher as well. But now it's using a single Vision Pro, and then going beyond just hands and arms, but also the other part of the body. Right, so some autonomous policy we train as well. It's the same thing. It's essentially now just extended with legs as well. So you can see the camera moves. So you can kind of need to observe the basket and then grasp it. And then when it goes to the other side, the head is looking at the other side, look at the basket, and then grasp it. It's all from egocentric observations, and then do this task. Right, so this is extending to the full body, and then more sim to reals, also applying dexterous manipulation. So this is a recent work that we do, basically try to do also hand manipulation, but now leveraging the simulation data. So this is more like training in sim with imitation learning, and then generalize and transfer to the real world. So I do think in the future, like simulation can provide you a lot more data, and then actually the contact is accurate for the models, for the hands and interaction with the objects, but there's physics gap. On the other hand, real world egocentric videos has rich visual, but then the contact is not so accurate because the contact from human hand and robot hand are still different. And then the physics still have gap. So at least I think simulation is not real visual, accurate contact, but the physics is bad. So you actually have different ticks and cross in different boxes in the whole thing. And I think actually the combinations of different data can actually help us to solve different boxes in this problem. Okay, I think that's all. Let me know if you have any questions. Thank you.